In 3.4, we're going to look at some applications of determinants. We've already seen one application, and that's determining whether a matrix is invertible or not. But we're going to look at three other things in this section. One is finding the inverse when the inverse exists. Another is going to be using Cramer's rule to solve systems when the determinant is non-zero. And we're also going to look at finding areas and volumes. All right, so first up, let's look at the section that says finding the inverse using an adjoint. I probably should have said using an adjoint and the determinant, since that's what this section is about. We've already seen this for the 2x2 case, and I want to talk about that a little bit here. In the 2x2 case, if you've got this matrix A, B, C, D, the adjoint, which is denoted like this, is this matrix. We've swapped A and D, and we've negated C and B. And if the determinant is non-zero for a 2x2, well, if the determinant is non-zero, then A inverse is equal to this, 1 over the determinant times the adjoint. Now, we saw this for the 2x2 case before, and the determinant, or the adjoint for larger matrices, is defined in the book if you want to look at it. It's the method for it is similar to cofactor expansion. But I don't want to spend a lot of time on this because this is not an efficient way to determine the inverse. But it can be useful because it gives you a formula for the inverse. And it's good to know about it even if you're not going to use it. I do want to take a minute though and talk about this note right here. One consequence of this formula is that if the matrix A has all integer entries, then the denominators of the inverse will be factors of the determinant of A. And I want to look at this with two different matrices here, M and N. I'm going to pull octave up, and I've already typed these in. So here's the matrix M, and if we take its inverse, let's see, inverse of M, looking at it, we've got a bunch of decimals, so let's change this to rational. Look at its inverse again. Notice all of those denominators are 17. And if you look back up here, the adjoint is multiplied by 1 over the determinant. So the determinant here, I would expect it to be 17 or possibly negative 17. Let's look at another example. This N matrix. Here's N, and if we look at its inverse, we get this. There's a star there. We'll talk about that in a minute. But all of these, 4s and 2s, that makes me think that the determinant is probably 4 or negative 4. Now, it's possible it could be 8 or 16 or something like that, something that 4 and 2 would both go into. But if we look at the determinant, yeah, it's negative 4. My cat has opinions on this. Let's see. Oh, what about that star there? Well, let's look at the inverse again. It gives us that star. What that star really means is 0. And let's change back to the short format. If I do that and I get the inverse, look at what it gives us here. This, where the star was, it gives us negative 4.166 times 10 to the negative 17th. So again, we're getting some sort of a numerical round-off error, and the star there indicates that the answer is 0, but there's some numerical issue there. So anyway, that's really all I want to talk about in this section, in this part of this section.